Caroline Grant from the Reynolds Group.
Good morning. So right now I'm going to talk about something completely different than what was just discussed. I'll be talking about how we can understand the parameters that control phase separation in organic photovoltaics. So this is part that was mentioned in the Reynolds Group looking at organic photovoltaics. And so when we look at organic photovoltaics, kind of the first advantages compared to inorganic silicon cells are the fact that they're lightweight and they're flexible. But then you also have the fact that you have layered structures that you can have a roll-to-roll process. And the fact that you can have these layered roll-to-roll process is really one of the biggest advantages for photovoltaic cells. And so in these layers, then, what we have is a transparent electrode where the light can come through. It can be absorbed in the active layer blend. And then we have the process, an electronic process, that can lead to charge generation. And so if you take the example of a polymer fullerene blend, then, for example, the light can be absorbed in the polymer, it creates an exciton, and then that exciton then has to diffuse to an interface with the fullerene in order to get charge separation and charge generation in these devices. And so then what's important is the phase separation between the polymer and the fullerene end devices. So what you're seeing here is kind of a cross-section of the whole device, showing that we have polymer-rich domains with fullerene-rich domains, and we can have mixed domains at the interface. And this is just a cartoon, right? But we can actually image this in cross-sections here, where we see the different layers. And what you can observe is that in the active layer blend, we really have very little control over the phase separation. It seems very random. And you can also see that on the surface topology through atomic force spectroscopy. So then, several tools that we can use to control the morphology are in terms of the polymer structure, for instance, where we can control the backbone by choosing the arrangement of donor and acceptor that we use for light absorption. But we can also play with the side chain that we choose. So, for example, moving the branching point away in order to induce better overlap between the polymer backbones. And we can also play around with the molecular weight or the end groups of the polymer. Now, this is a structure processing property relationship. So processing also impacts very much the resulting properties that you observe. And you have different ways that you can choose, different tools that you can choose. And so you have technique, for example, looking at spin coating versus bake coating. And then one big aspect that will change your morphology is the solvent choice. So today, the two aspects that I'll be focusing on are the choice of the side chain and the molecular weight on the structure side, and then looking at processing additives on more of the processes. So the polymer system that we're using throughout the study is this terthiophene coupled to isoindigo. So we have the electron-rich unit and then electron-poor unit alternating, so that gives us the light absorption properties that we want for organic photovoltaics. And in the first part, we're playing around with the side chain on the terthiophene unit in order to modify the solubility of the resulting polymer. And the questions that we're trying to answer here are, structurally, on the polymer, what can we change in order to control the morphology, and then how that morphology then can impact the macroscopic properties. And then in terms of processing, then we'll just look at one polymer structure and add different processing additives while we fabricate the device to see how those then control the morphology, and how that morphology can then in turn control the macroscopic properties. So in terms of how these polymers were synthesized, we used stilly polycondensation to yield a family of 6 polymers with different side chains. And so you can see that we can change the solubility of the polymer by changing the length of the side chain. We can also change the solubility by changing the molecular weight of the polymer. And then one important aspect is changing the branching point. So by using a 2-ethyl hexyl chain, we're able to torque the polymer backbone, and that again increases the solubility, and that's what we see here, that we're getting increasing the solubility. Now, because these all have the same backbone, we typically see the same film absorption in the film, which is good to compare properties in the So looking at these polymers in OPV devices, then we're using the 6 polymers in different blends with the same fullerene, spin coating from the same solvent orthodeck chlorobenzene. And we can see that looking at the current density versus voltage curve, which is a measure of how performing these devices on. We have really little change in the short circuit currents and the open circuit voltage. You can see here the statistic difference between the different polymers is very little, apart from when we come to the 2-net hexyl polymer here, it's very soluble. And so when we use this polymer in the blend, you can see a large decrease in the short circuit current, and that's what we also see in the external polymer efficiency. And so now we can correlate these properties to what we're seeing in the blend morphology. And so for the polymers where we always have linear side chains, we're seeing the same type of morphology where we have very fine phase separation between the polymer and the fullerene. However, when we use the 2-eclohexyl polymer, then we're seeing these large fullerene aggregates that are embedded within the polymer film. And so this change in the morphology then can be correlated to the fact that we're seeing very poor current density in these devices. And so what we kind of outline is that when pi interactions between the polymer chains are made accessible, we can get to this fine phase separation. But when we hinder the pi interactions by having these torque backbones that are induced by the steric of the side chain, then we're allowing the formation of these PCBM aggregates, and that then dictates the morphology in the thin film. So when we have the morphology like this, it's not the end of the world. We can play around with processing in order to get the final morphology that we desire. And we've shown this previously using another isoindigo polymer. When we spin cast it from fullerene or chlorobenzene, we see again these large domains in the film. But when we add a small volume percent of a 1,8 diodooctane in the film, we can drastically change the morphology. And again, we can correlate that to what we're seeing in the device, where we see a large increase in the short circuit currents. Two types of mechanisms have been proposed to explain how these processing additives work. One of the mechanisms involves the fact that when using a single solvent, we have large fullerene aggregates that then form large domains within the film. But when we use diiodooctane, then we break up the fullerene aggregates and they're able to penetrate further into the polymer domains, creating a more mixed and finer phase separation. Another proposed mechanism is based on chloronaphthalene as a processing additive. And in this study, the authors showed that you're actually creating more ordered polymer aggregates in solution. And so then, as the film dries, these aggregates then act as nucleation sites for the formation of polymer fibrils. And that is what dictates your morphology in the thin film. And so what we did here was to look at one polymer fullerene system that is cast from the chloroform, and we add small volume percent of these different additives. And so you can see that structurally, these additives fall into two categories. Some of them are aliphatic additives, some of them are aromatic additives, and we can also change the functionality of the additives, looking, for example, at non-functional additives, monofunctional, and then bifunctional here. And so what's interesting is that, again, very little change on the open circuit voltage, but drastic change in the short circuit currents, and we can kind of outline two different domains for these processing additives. One where we see no improvement compared to the pure solvent chloroform, and then one where we can see an increase in the short circuit current. And again, looking at the phase separation through AFN, we can see that using chloroform as the casting solvent, we have again these large domains, which lead to the poor short circuit currents. When we're using hexadecane or iodoctane, we maintain those large phase separations, so we really don't see any change in the short circuit currents. But when we go to bifunctional additives, that's when we see the large change in separation. And we observe that, again, the same change when you're using aromatic additives. And so in conclusion, kind of the two parameters that we can outline that control the phase separation in the polymer fullerene blends are the fact that we can control the phase separation through the structure by allowing the polymer chains to interact with one another and form these polymer fibrils through pi-pi interactions. And on the processing side, then, we can outline some structural parameters on the processing additive that will dictate the phase separation. So looking at the aliphatic additives, we notice that we need to have a bifunctionality of the additive in order to induce that finer phase separation. And in the case of aromatic additives, no matter what type of functionality you have on the rings, you really get an increase in short circuit current density. And so in this case, it's less sensitive to the functionality than it is to the aromatic nature of the processing additive. with that, I would like to thank Dr. Reynolds and the Reynolds group members who came in numbers today, so I really appreciate that. I'd like to thank COPE for support, as well as the Georgia Tech Polymer Network, AFR's ONR funding, and thank you for your attention.
Very nice. Any questions?
So when you're looking at these domain sizes, do you guys have a targeted goal for what you like to see as the ideal sizes? I know it was when you got around like 10 nanometers, diffusion length and stuff like that.
Right, so kind of the random, or not random, but the target number is 10 to 20 nanometers. However, there's been recent work that has shown that you do see a difference going from polymer fibrils that have a width of 4 nanometers all the way to 10 nanometers. So even below 10 nanometers, you do see an impact of the polymer domains. So basically the target is as small as you can get it while maintaining all other properties that are desirable at church.
It's too small, sometimes bad. Is there a way to...
I'm sure it is, because I guess you do still want to have a continuous network throughout your film. So even if you do, if you're able to get very thin fibers, I guess all the way from one end to another, or from one end of the device to the other, that would be fine. But I guess it's difficult to control the orientation in that case. And in that case, then if you don't have a continuous network, too small may be detrimental.
Because in the data you showed, you know, these different additives,
Yeah.
there's the first group, the materials that kind of give you the same domain size, right? So
The difficulty here is quantifying the domain size. So because we're only having AFM data, we're only looking at the top surface, and we really can't quantify the size of the domains. I think by looking at TEM, where we can actually quantify it, that would be a very nice way to see if there is a trend in the domain size, and if we can correlate that to how small it is too small, or if there is a limit on the size.
any other questions? If not, then let's thank Caroline again.